runtime is the average execution time of F measured by profiling this resulting binary on some benchmark scenarios with tolerance epsilon. And we are trying to minimize the size of this specific function while maintaining constant execution time. So the current research gaps are that, first of all, this approach called phase ordering applied is mainly research for LLVM. There was work for GCC, but it's largely outdated. Then secondly, compiler auto-tuning research usually studies single objective functions. So for instance, usually only code size is optimized or execution time. But in practice, multiple objectives are important because for instance, embedded systems, they are constrained in memory, but they also have certain runtime requirements. Next, most auto-tuning research studies whole program tuning, but in our work, we study function level tuning because it proves to have lower tuning costs. And then to date, the space exploration frameworks are quite limited. And again, they are tuned for LLVM, and they are not suitable for exploring constant execution time. Then finally, the current benchmark suits, they are either limited because they are collected for some, they're just a set of field tests, or they are massively collected and mined. And usually these mined tests, they're not even executable, while the first tests, they are not suitable for our objective function. The research questions we are answering is, first of all, how good is GCC's O2 default function level optimization sequence compared to randomly chosen sequences, which we explore? And then how is the probability of finding a good function level optimization sequence distributed across functions? So to answer these research questions, we developed a space exploration framework. In order to explore space optimization sequences in GCC, we developed a phase ordering plugin, which will be described in the next talk by my colleagues. Also, a shuffler library was developed to generate optimization sequences, and my main contribution is developing a coordinator tool, a scalable coordinator tool for compiling benchmarks and profiling them to perform a big number of experiments. So our benchmark suite called multi-benches, it consists of open source suits like cbench, LLVM test suits, spec, and also it consists of open source programs like ZSTD, JIP, gzip, and each benchmark has a list of feasible functions, feasible in terms of our objective function. They must have an appropriate runtime that's more than 0. Also, each benchmark has input data. So for instance, for ZSTD, it's some file to be compressed, and then it has a number of repetitions to reduce variance and some other noise during measurement. In our experimental setup, we used modern GCC version 7.3. Our target architecture is Arch64 because, again, the main application of this work is for embedded systems. So we had to use QEMU for emulation. And then we evaluated this on the multi-benches suite I just described. So in our experimental setup, we chose sample functions in each benchmark. We applied a random sequence to this sample function, while the rest of the functions, like the default O2 sequence was used for them. And then we compared the results to a baseline where all functions were compiled with the default O2 sequence. So we applied 50 such experiments of unique random optimization sequences. Each consisted of 65 elements, each optimization sequence. This is basically the base set of optimizations, function level optimizations available in GCC. And then, yeah, as I said, we applied the O2 default optimization level to the rest of the functions except for the sample function. We used this 3-category classification for evaluating our results. So as you can see, we account for the sample size compared to the baseline size, as well as the samples runtime compared to the baseline runtime. We conducted, in all, we conducted 8,500 experiments. This histogram shows the results. And as we can see, for most of the functions, this GCC yields, we didn't get a better result, but there is a number of functions for which we received better results. So to generalize the result we received here, we formulated this theorem that the probability of a random function level optimization sequence to beat GCC 02 is in the interval of 9.1 to 9.5%. And this probability is at least 90%. Basically, this is just a corollary of Chebyshev's inequality. The benefit of our approach is that we can conduct a large number of statistical experiments and get a histogram like this. And this allows us to generalize the results using means of statistics. So the theorem seems to imply that GCC's O2 functional optimization sequence is not perfect because there's 9% of chance to beat it. So we have to note that this heavily depends on the distribution and on the benchmark suit we use, this result. So in order to actually answer our second research question, we need to analyze the distribution of our results. So here we plotted a histogram of winning and losing probabilities, winning probabilities on the left and losing on the right. The x-axis is divided into 10 bins of how many winning or losing sequences there are for the given number of functions. And the y-axis shows the number of functions for which at least one random optimization sequence out of 50 outperformed. So here we see that though 0 out of 50 sequences won O2 in 152 functions, there were from 40 to 50 of the random sequences that won O2 in 16 functions. So we can restate this result as that GCC is efficient for most functions, but as we predicted in our hypothesis, there's a set of functions for which it is not, it is suboptimal, and there's space for optimization and improvement. So the further research directions we propose is, first of all, using collaborative interactions and dependencies among optimization passes. So some optimization passes can benefit when they are applied after certain other ones. And there's also an approach called collaborative filtering, when the optimization space is reduced to certain subsequences, which prove to be efficient in against statistical tests. Then the second research direction is using guided space exploration. This will be discussed by my colleagues in the next talk and this conference. Here, approaches like genetic algorithms or reinforcement learning can be used to explore the optimization space, because obviously using random sequences is not efficient. And then finally, the most interesting thing is adaptive compilation strategies. So here we just explored that using random sequences, we can get better. We got the result that GCC's fixed optimization sequence is not optimal for some functions, and we could employ adaptive compilation strategies that could account for these edge cases. So to conclude, in our work, we developed a space exploration framework for exploring optimization sequences of a modern GCC compiler. Our evaluation showed that there's 9% chance of outperforming GCC with the random optimization sequence. We formalized this statistical result into a theorem. And then further analysis of the distribution of our results showed that the default optimization level is good for most functions and poor for a select few. And then finally, we proposed further research directions. I guess this is it. Thank you for your attention.
Thank you for your report. My name is Mark Mamchenko, Institute of Control Sciences. I have a question. I'm sorry, I'm not a specialist in this topic, so maybe my questions are maybe incorrect, but
sure.
There was a slide with research gaps, and can you tell how do your results correspond with these gaps?
Yes. So first of all, as I said, most compiler auto-tuning research focuses on LLVM. There is research focus that studies GCC, but it studies flag tuning. Flag tuning is basically selecting optimizations, and here we are reordering them. So we studied the GCC phase ordering problem for a modern GCC compiler because there was previous research, but it's largely outdated. It was in like 2010, and GCC has significantly changed since this time. Secondly, as I said, most compiler tuning research uses a single objective function, like they only study code size or only study execution time. But here we have multiple objectives. We study code size constrained by execution time. Then mostly the topic of auto-tuning is whole program tuning and function level tuning or tuning at other like fine-grained other like levels of abstractions is not that covered in literature. So here we studied function level auto-tuning. Then, as I said, current available space exploration frameworks like compiler gym or in the paper we also mentioned Yakos. They are compiler gym is more suitable for reinforcement learning, and it's not as suitable for random exploration. And the other framework, it's more applicable to. They both fit more for LLVM. Yeah, and then finally, the current available benchmark suits, they, as I said, are massively collected, so we can't use them to evaluate our objective function because they're not even executable, or they're just like quite limited, and they're not. They're limited in the sense that again, they are not. They need to be tuned for our objective function, which we did in multi-benches. I hope I answered your question.
Yes, thank you.
Okay. Does anybody have any questions?
Thank you for your presentation. Taras Fuly, my PT. You compared random sequence with O2
yes.
level. Why did you choose this optimization level? Why not OS, which is designed to compile small binary when O2 can?
Well, because
with O2, were any performance comparison with your code?
Could you please elaborate the second question? What do you mean by performance comparisons? Oh, okay. Let me. So you see here we had part of our evaluation criteria, like whether the result is worse, equal, or better. We compared the execution time of the sample function compared to the execution time of the baseline. So the baseline was compiled with O2. The sample was compiled with a random optimization sequence. So yes, we compared the performance. The reason why we use O2 and not OS is because like our goal is to like let's return to our research problem. Our goal is, first of all, to optimize, like to have efficient binaries, but then because like that's a requirement in industry. Everyone compiles O2 because there are runtime constraints. There are timing constraints and real-time requirements, and we just want to improve the binary size, so we want to reduce it. But our main goal is still having optimal execution time and trying to leave it constant. So our main objective is still runtime, but having it constant, we want to try to improve the size of the binary and reduce it. That, I guess, I hope I answered your question.
Okay, I think that it's over. Very good work. Let's continue with next. Who is the next? Okay, let's continue with Artem Manilov. Automated design optimization for the 2RPR parallel robot.